In this video, we are going to go over section 10.4, which is approximation using Taylor series. We have already seen approximation, so using the Taylor's polynomial. So back in chapter 10.2, and I can refer a problem that we did it together. 10, maybe it was 10.1. Oh, right over here, number 4 on 10.1. What we did was we we come up with a Taylor polynomial right over here that we circle, plug it in and get a value 1.2839, and the actual polynomial of cube root of 2 was 1.2599. So we used the approximation, and then you can kind of see the error, little bit of an error, because really it is 1.2599, but we got 1.2839. So that's what we are going to be working on in 10.4. In 10.4, we're going to approximate it and then find this error bound. So we have this remainder term, whatever the function f of x minus the Taylor polynomial will be how much we are off. We call that the remainder term. You can also modify this equation. Let's say if I added p of x each side, then you can also think of the actual function is the Taylor polynomial plus the remainder part. Either one is okay. The error, that 1.25 versus 1.28, that can be approximated by simply subtracting and then take the absolute value to keep it positive. So that's the remainder of the Taylor series. Formula, you can do it that way, or you can directly find the formula for the remainder term by using the derivative term. If f has a derivative of all orders at 0, then the remainder term of the Taylor polynomial is f of n plus 1 derivative of t x raised to n plus 1 divided by n plus 1 factorial for some number t between 0 and x. Theorem, error estimation for alternating series. So for error in the alternating series, we have a function here, and then if the term alternates, then signs and decreasing absolute value. So we can also take an absolute value and then keep it positive. So I'll show you how the theorem can be used. Right now it looks just a bunch of letters, but we will apply the theorem when we actually work on the problem. So I have 4 problems to work on. So let's begin with number 1. Use the third degree Taylor polynomial f of x e to the x to approximate e raised to the 0.5. So we have to come up with a Taylor polynomial and then approximate e raised to the 0.5. And use the Taylor formula for the remainder to estimate how much we have in error in this approximation. So f of x is given. F of x is e to the x, but this can be interpreted as p of x polynomial, Taylor polynomial plus the remainder term. So, and this is a degree 3. So you can rewrite that as a p Taylor polynomial of third degree and some remainder term. Okay. Well, we know that e to the x Taylor polynomial, right? From table 1, chapter 10.3 from the PowerPoint, e to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus e raised to the t x to the 4th over 4 factorial. I'm talking about this one over here. Right there, e to the x. Okay. All right. So Therefore, we want to take a x value 0.5. So f of 0.5 is p of 3 0.5, right? About p of 0.5. So I have directly plug it in here. I'm getting 1 plus 0.5, 1 over 2 factorial, 0.5 square, 1 over 3 factorial, 0.5 cube. Technically, it's degree 3. So we consider plug it into the 3 terms. Okay. I just wrote a couple more, but we just need a degree 3, so we stop at the 3rd term. So just doing some little bit of algebra, 1 plus 0.5, this is 0.125 plus 0.020833, all adding up, I get 1.6458 as our approximation. Okay. So nothing too different than 10.1. Now, the problem asks you, if you actually look at E, if you want to check, E raise it to 0.5 is 1.6487, 1.6487. So you can see that actually E raised it to the 0.5, 1.6487. We are a little bit off. We got 1.645. We were 2 decimal place accurate. And then the 3rd decimal place, we got 5 instead of 8. So there's some error. Now, let's estimate that error. So the error is given by the last term in the polynomial. How do you know? Because that's what we wrote. P sub 3, the setup was P sub 3, and then the last term is your remainder term. That's the error term. So therefore, E error is R sub 3 of 0.5. And you can, I'm just following here. That's your error bound, which is R sub 3, 0.5. And you can do this by finding this part over here. So R sub n is f of n plus 1 sub t. So that's E sub t. X, which is 0.5, raise it to the 4. We go one more. 3 was our nth degree, so 4, 3 plus 1, and then 4 factorial, 3 plus 1. So that's your error bound. E to the t, that's your function, right? E to the t, 0.5 to the 4th over 4 factorial. Okay. And then let's pull out the calculator and then do some algebra. So I will enter it on the calculator and see what I have. E raise it to times 0.5 4th power divided by 4 factorial. Okay, I'm getting absolute value of 3 over 384, which is equal to 0.0078. So what does this mean? This means you have, we can conclude that approximation value of 1.6458 is within plus or minus of 0.0078 of the exact value of e to the 0.5. So I will write one more sentence. We can conclude that the approximation value, that was our approximation value, 1.6458 is within plus or minus 0.0078 of the exact value of e to the 0.5. Okay. All right. Then let's continue. Another approximation. Use the Taylor series of ln 1 plus x to approximate 1.4 with no more than 0.0005 error bound. All right. So now they give you error bound. Earlier we found the error bound, but we want to approximate it, so there's no more than, we are no more off than 0.005. So let's come up with the Taylor polynomial. This is something that we know from table 1 section 10.3 that's given about the Taylor series. So table 1, 10.3, we know that Taylor series for ln 1 plus x is x minus 1 over 2 x squared plus 1 over 3 x cubed all the way up to, actually the sign alternates, so it should be minus, plus negative 1 to the some power k x to the k. We have it centered at 0, and then we have 1.4. So we want to substitute x as a 0.4 since 1.4 is x plus 0.4, right? Whatever the x is at 0.4. So f of 0.4 is ln of 1 plus 0.4. That's because you have 1 plus 0.4 to give you 1.4. So that means I'm going to be substituting wherever you see x as a 0.4 on that above polynomial. So that's 0.4 minus 1 over 2 x squared, which is 0.4 squared. Next term will be 1 over 3, 0.4 cubed. Next term will be the fourth, 1 over 4th, 0.4 to the 4. And then I'm just gonna keep going. I don't know how many terms. Notice that it's not giving you the degrees, so I don't know. So I just keep going to grab more and more decimal place and check and see if that's no more than 0.005. So let's just go one more. 1 over 5. I don't know how many degrees it takes for Taylor polynomial so that there's error bound within the 0.005. So I just decided to go 5 terms. Might work, might not work. So changing everything into the decimal, I'm going to have a 0.4 minus 0.08 plus 0.0213 minus 0.0064 plus 0.002048. Those are my decimal points. So if we do that, since the absolute value of the terms are decreasing, we can apply theorem 1 the first four term represent the approximation of the fifth term, represent the error. So this part will be my error term, right? Because remember the formula is f of x p sub n x plus the remainder term. And this one will be your Taylor polynomial of the first four term. That's how you interpret it. Right? Okay. So your error, take a look. You want it no more than 0.005. This is no more than 0.005. See, if you stop here on the fourth term, you know that this will be your error term. And notice that that's more than 0.005. So that's how I know that I need to go extra term, because your last term will be always your remainder term. And look at the number. That's a 0.002, which is less than 0.005, because we don't want to go more than 0.005. So I know that the fifth term is my necessary term. Okay, so my error bound is 0.002048, which is less than 0.005. That's good. So your ln of 1.4 approximation will be just these one using the Taylor polynomial, and that value will be error less than 0.005. In fact, 0.002048. So let's sum that up. 0.4 minus 0.08 plus 0.2013 minus 0.0064, which is equal to 0.3349. Done. Okay. Number three. Now, number three give you a different layout, but same thing. They give you the integral, so that means I probably have to integrate and then come up with the polynomial. Okay. Again, this e to the x squared, I'm going to be using the table 1 to come up with my basic one. So we know that 10.3 table 1, we are given e to the x is 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, all the way up to 1 over n factorial x to the n. And our actual f of x, that's your f of x, which is e raised to the x squared, I'm just basically substituting the x into x squared to come up with my polynomial, Taylor polynomial. So it will be 1 plus, instead of x, you have x squared. Everywhere you see x, you're going to substitute x squared. Plus 1 over 2 factorial, x squared square x to the 4th, 1 over 3 factorial x to the 6th, all the way up to 1 over n factorial x to the 2n. Now to find our, that's your integration underneath, so I need to take the derivative, okay? I need to integrate it so that I just have a single f of x. So integrating this whole thing, one over 3 factorial x to the 6, 1 over n factorial x to the 2n dx. Again, it's that's an indefinite integral, so I'm gonna put the constant term first. X will be just x. 1 will be x. X squared will be x cubed over 3 plus x to the 5th over 10 plus all the way up to this one will be x raised to the 2n plus 1 and factorial divided by new power 2n plus 1. let's consider that constant value be 0 and approximate the integral because we are not given any other information. So let the constant value be 0 and approximate the integral. Okay. Then I will be adding a page. Okay, so let's continue. So you have 0 to 1 right over here. I erased it, but we are considering 0 to 1 of e to the x squared dx. We already take the antiderivative right over here. So that will be your f of 1 minus f of 0. So doing that, I'm going to actually copy this one, considering constant term as a 0. Right here, let's put that. Just copied. Okay. Let's plug it in 1 and 0. So if I plug it in 1, I'm going to have 1 plus 1/3 plus 1 over 10 all the way up to x. I'm plugging in 1 here, so 1 over n factorial 2n plus 1. Minus 0, because 0, if I plug in a 0, this will be 0. 0 over divided by 3 is a 0. 0 divided by 10 is 0. 0 over anything is a 0. So I have this. So all I have to do is simplify this. 1 plus 1/3 plus 1 over 10. The next term will be 1 over 42. Next term will be 216 and so on. So let's go back. I want 0.005. Again, now just like last one, you have to look at into decimal and see which term on the last one. I don't know how many polynomial it needs because it didn't give you the degree. So I just have to check one by one and see which the last term end up being less than 0.005. So this is 0.3, which is too big. Remember, we want 0.005, right? 0.005, yeah. So 1 over 10, changing to the decimal, that's 0.1. This 0.3, repeat it. 1 over 42, that's a 0.02. We are getting smaller, that's good. 1 over 216 is 0.0046, so that's good. 0.005. So that's where I know that this is my error bound. So we just need first 4 term of the Taylor polynomial. So since the value 1 over 216 is about 0.0046, which is less than 0.005, that's what we want. We need Taylor polynomial of the first 4 terms. We just need to consider the 4th term. So we just add them up. 1 plus 1/3 plus 1 over 10 plus 1 over 42. We end up having, rounding to the 3 decimal place, I got 1.457. Okay? So just go through. We don't know how long it takes, so just keep adding term until you are close to that boundary value. All right, last exercise. Last exercise is approximate the index income concentration for Lorentz curve given by f of x, 15x to the fifth power divided by 20 plus x squared with an error no more than 0.005. Now, let's recall one thing that you have to know is what is a Lorentz curve, and then this is a section 6.1 on your textbook. So Lorentz curve, so recall the formula for the Lorentz curve from section 6.1 is the formula is 2 integral, and I'll show you. I actually pull out chapter 6 Lorentz curve right here. Equation for the Lorentz curve from the Gini index. 2i's of 0 to 1 x minus f of x dx. 6.1. 0, 1 x minus f of x dx. So I'll use that in a minute. Okay, let's begin from the beginning. What do I have to know? I have to first approximate this function within no more than 0.005. So let's begin that. So that's so this is my Lorentz curve. By the formula, I can separate the integral. So this is 2 integral 0 to 1 x dx. I just like separating, and then 2 twice of 0 to 1 f of x dx. So we know I'm just going to move this one so you can see the integral clearly. You can always move in and out about your constant term. So moving back, you have 2x dx, and then also you know this whole thing is your f of x, and then if I move the 2 inside, I'm going to have 30x to the fifth over 20 plus x squared dx. Okay, let's take the integral one by one. This is a very easy to integrate, right? This one requires a little bit of thinking. This one is a Taylor polynomial. U substitution will not work. You can try it, but it's not a simple one. So we need a little bit of a work to do for the second integral. But the first one is easy, so let's begin with that. This part over here, I have 2x dx. So your derivative is x squared. Actually, I'll use it on the side. So 0, 1, 2x dx. This will be x squared over 2, 0 to 1. So it will be 1 squared. Right? And then minus 0 squared, so which is 1 minus 0 equal 1. So this whole thing is just 1. Now, this one requires a little bit more work, so I'm going to be working on the side. Now, if you look at this one, this is also a Taylor polynomial with a little bit of an extra. So 30x to the fifth over, this is a little bit of a side work, over 20 plus x squared. That's really 30x squared over 20. 1 over 1 plus x squared over 20. Now, why did I bother to write it out this way? Because this is our Taylor polynomial. We have something like this given. Right over here, you can see 1 over 1 plus x terms. So I'm going to be using the Taylor polynomial so I can integrate it easier by term. That's the whole purpose. So using the table 10 table 1, 10.3. I'm gonna rewrite it. And then 30 divided by 20 is, I'll just change to decimal so it's easier. I don't like fraction. This part using the Taylor polynomial table, I have 1 minus x plus x squared dot 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 plus negative 1 raised to the xn. Excuse me. X to the n. But that's just 1 over 1 plus x. I need to replace the x with x squared over 20. So this is how our modification of a equation. So instead of x, I put x squared over 20, and then you have that x squared over 20 square, right? Everything that you see as an x, you're going to write it as an x squared over 20 raised to the n. Let's distribute all the 1.5x squared. So the first term will be x to the fifth. 1.5 x to the fifth minus 1.5 over 20 x squared with the x to the fifth. I have x to the seventh. That's 20 squared on the bottom, and then 1.5 over 20 squared x to the ninth. Then last term will be 1 over 1.5. 20 raised to the nth power x to the 2n plus 5. Okay, because there's 2 and then n, multiply and then plus 5. Let's add another page. Couple things before we integrate. The initial radians of convergence was from the table, it was between -1 to 1, right here. -1 to 1. But instead of x, we use x squared over 20. So let's calculate it. Multiply 20 each side, and then square root, and then modify. So I have -2 root 5x -2 root 5, and then +2 root 5. So that will be your radius of convergence. Now we are ready to integrate the 30x to the fifth, 20x squared dx. And then I'm going to copy this whole expression. That's what and then integrate it. That's what we are doing here. We need to integrate this whole function. So I need to integrate this. Okay. Integrating is pretty easy now because term by term, right? So what's the first term? Raised power divided by nu. So adding 1 more to the 5, 6. So 1.5 over 6, x to the 6. Next one, 7th, now raise it to the 8th power divided by nu. Power, x to the 8th, 20 times 8. Next one, 1.5. Now the new power is 10. So 10 times 20 square, all the way up to 1.5. And then you have that, if I raise by 1, adding 5 plus 1 will be 6. So that's my new power, 2n plus 6, 20, raise it to the nth. Okay, what are my numbers? 0 to 1. So I need to evaluate 0 to 1. Now, fortunately, all the zeros will cancel out. So all I have to do really, f of 1 minus f of 0. But this will be just a 0. So I just have to find out f of 1. So plug it in. 1.5 over 6. And then 1 to the 6th power is just 1. 1.5, 160. 1.5 over 4,000. All the way up to the last term, 1.5. And then negative 1 to the nth power, depending on negative or positive on the last term. And then 2n plus 6, 20n. Oh, I think, yeah, when I write it the last term, I forgot that negative 1 raise it to the nth power. All right, just getting the decimal for each term. I have 0.25 minus 0.009375 plus 0.00375. So I'm getting approximately 0.241, rounding to the 3 decimal place. How did I know, again, to stop at the third term? They give you. Number 4 says error by no more than 0.005. 0.005, we want that less than. So this term right here is less than 0.005, so that's your remainder term. Okay, so that's your remainder term. So that means but we are not done. Remember your whole equation. Let's go back. Don't forget it was this one. We only needed this part here. So let's actually calculate that. Because remember I separate the terms. So I'm going to go back and then add this. So don't forget our original equation was this. So this was 2, 0 to 1, x minus f of x dx. And you know that I'm going to be putting this one for the last one. So that will be 0.241. So my final answer is approximately 0.769. All right, that's it for chapter 10. And we finished completely on chapter 10, Taylor polynomial and Taylor series.